Hello, good morning. So please take your seat. Thank you very much. So thank you all for coming. So yes, let's wait that all the colleagues take a seat. Thank you so much. So welcome to the Christmas lecture of the Astrophysics campus in Bologna, 2024. So on behalf of INAF OAS, INAF ERA, and the Department of Physics and Astronomy of the University, I welcome you. Today we are pleased to have as a speaker Professor Maurizio Spurio from the University of Bologna and the INFN in Bologna, so a main expert in astroparticle physics and neutrino astrophysics. So Maurizio, so Professor Spurio was an expert working on neutrinos, on the macro experiment in Gran Sasso, so participating to the discovery of oscillations of atmospheric neutrinos. Then he collaborated with very large astrophysical neutrino observatories and cosmic rays, so Antares and NEMO. And now he's part of the Kilometer Cube Net collaboration, which is our main facilities for the future, for making a further leap in the fastly growing field of neutrino astrophysics. So again, I thank very much Maurizio for giving this lecture. And so I leave the floor to you. Thank you so much.
So first, thank you very much to be invited here. It's really a pleasure. I'm teaching very often to the close by building, so I'm sharing my teaching duties in the physics department in Vierneri and here. So it's the first time I talk about my research activity here. So I tried today to show which is the field of neutrino astrophysics connected with, of course, the world of astrophysics done with the electromagnetic radiation, the role of neutrinos, and also how the experiment can be constructed and realized deep in the sea or in the ice. And finally, I introduced a more recent, a new experiment, which is the KM3net experiment, and some exciting results which we found just analyzing the very really first data set. So I worked in cosmic ray physics since my PhD activities and Laura thesis in the mid of the 80s. And I understand that there is another way to study the universe using the probes, which are individual particles, which can be used in addition to the electromagnetic radiation. In particular, the electromagnetic radiation is mainly produced close by to the source by electrons. So we cannot see many electrons of very high energy arriving on Earth because the electron lose energy close by to the source and they emit electromagnetic radiation from radios to X-ray, which is the field of astronomy, of course. Then there is the possibility to study the high-energy universe also using the individual probes, for instance, cosmic ray, also secondary antiparticle, which can be produced by interaction of cosmic ray and neutrinos, and also gamma rays. Gamma rays is a sort of particularity in the electromagnetic radiation because they must be measured and detected with individual particles as for instance, a neutrino or a charged cosmic ray. In between the two activities done by astroparticle physicists and astronomy, there is the activity very recent due to observation of gravitational waves, which use some technique which are in between, common between the two fields of astronomy and astroparticle physics. In particular, I have to mention what electrons produce most of the electromagnetic radiation, while protons are the subject of the main of activity connected with individual quanta. Neutrinos are produced by proton interaction and also gamma rays, and also massive objects. So essentially protons are the origin or other massive particles are at the origin of gravitational waves. Concerning neutrino are produced, exist in the universe in many order of magnitude. In this plot, you can see in the x-axis the energy of neutrinos. We expect to have a very large number of neutrinos of cosmological origin, like the microwave radiation of 3 Kelvin degree, but those neutrinos have never been observed. While neutrinos have been observed coming from the sun at the energy of order of magnitude 1 MeV. This is one of the first triumphs of astroparticle physics because you join the knowledge of the sun properties observed by different tools by astronomers with the fact that the energy is produced inside the core of the sun and produce neutrino, and those observations are supported and demonstrated the process of fusion reaction inside the star. Another field in which astroparticle physics and the conjunction between observation of probes and electromagnetic radiation have a very important role is connected with supernova explosion. In particular, this plot shows the energy distribution of neutrino from supernova. This is the overall sum of all neutrinos produced by the expected supernova explosion in the universe. This dashed line is the burst produced by one supernova event, means neutrino in about 30 seconds. And this is the observation done in 1987 by the Kamiokande MBB experiment. In particular, I want to mention that the Kamiokande experiment, which observed the 12 events from the supernova in 87 in February, was started in operation in January 86, 1 year before, and just in December 86 is decreased the threshold of for detection in order to be able to detect neutrino from a supernova. So it's an happy situation in which just 3 months later that decreasing threshold of neutrino detection, a supernova event occurred in February 87. Since then, there are we are waiting for supernova, but no supernova are occurred so far. So it's really important in order to have additional information about this process. Then at higher energy, there are atmospheric neutrino. Atmospheric neutrino was very important for particle physics because they demonstrated that neutrino are massive particles. And this is one example of the detector used in order to measure atmospheric neutrino, which is the Super Kamiokande experiment. Just to have an idea, is an experiment made by a huge tank of 50 meters of diameter and 36 meters of height. And then there is an additional, a new experiment, Hyper Kamiokande, which is still larger, which is in construction today in Japan. And then there are, at the very high energy, there are neutrinos of very high energy produced by some astrophysical source, either galactic or extragalactic, in which in a large fraction is superimposed to atmospheric neutrino. And because the neutrino interaction cross-section, the probability of interaction increase with energy, but the flux, which is the quantity plotted in the epsilon axis, decrease, you should have a still larger detector in order to have the possibility to measure high energy neutrinos. And this is the role of neutrino telescope as IceCube, which I will mention later. This is the summary of the all electromagnetic observation from extragalactic radiation observed so far as a function of the frequency of the energy. So the two communities I mentioned before, that of astronomy, probably is recognized by the fact that when looking at plot like this one, look the x-axis in which there is frequency or wavelength, while particle physics prefer to have a quantity as the energy in order to express this radiation. But I have to mention that this plot ends for concerning electromagnetic radiation of extragalactic origin up to, let's say, 100 TeV. There is no photons higher than 100 TeV from the extragalactic region. There are galactic, very high energy photons detected by some experiments, for instance, LASO, which are of galactic origin, but not from extragalactic. So there is this empty region, which can be filled, for instance, by cosmic ray, but there is one problem for charged particle and neutrinos. So this is, for instance, the summary of the observation in the last 10 years, so mainly from IceCube of this energy region. And again, when you see this plot as a function of energy, usually particle physics prefer to use a non-international unit measurement for energy. They prefer to use GV or TV. For instance, 1 TV is very close to 1 erg, so sometimes the two communities have this happy chance in a similar way. Why the connection between cosmic ray, gamma rays, and neutrino are important? Because there is the possibility to study the very high energy process in the universe, observing the secondary neutral particle. In fact, you have some acceleration process, either in galaxy, in our galaxy, or in extragalactic space. And of course, some of the accelerated particle can escape, essentially protons. I mentioned that electrons lose energy in order to make them visible close to the region of acceleration. This is the reason why you detect electromagnetic radiation from radio to X-ray, while some proton can escape, but the problem is that there are magnetic fields which deflect the direction of charged particles, so you cannot do astronomy looking charged particles because they do not remember the direction. But they can also interact, protons, producing secondary mesons. Mesons are decaying in different ways. If they are neutral, they decay into gamma rays, while if they are charged particles, they decay in neutrino and muons. So you have a production, simultaneous production of gamma ray and neutrinos, and the number is strictly correlated. So you expect roughly the same number of neutrinos and gamma rays, so very high energy. Gamma ray can also be produced by electrons with different process, from instance, from Brech-Strahlung, and also by inverse Compton, means that you have a radiation field of low energy or lower energy photons, and high energy electron can upscatter the photons, providing them very high energy, so you can have very energetic photons produced by accelerated electrons. The problem of very high energy photons from the extragalactic space is the fact that the space is permeated by electromagnetic radiation, for instance, that of the cosmic microwave background, and also from the extragalactic background light. And in this way, if the energy exceeds of the center mass of the two photons exceed that of the mass of the electron-positron pair, you have the creation of pairs, and it is occur, for instance, when you interact with the cosmic microwave background for photons with energy in the range of 10 to 100 TeV. So the flux of photons larger than 100 TeV from extragalactic space is strongly reduced or totally reduced by this interaction with the cosmic microwave background. Protons are deflected by magnetic fields, so essentially in order to test, to observe the very far universe, you have only neutrinos, and the only energy loss of a neutrino, which are very weakly interactive particle, is due to the expansion of the universe, the redshift of the energy due to the expansion of the universe. This is, for instance, on the bottom left is the, as a function of the energy, the length traveled by photons, which can interact with the infrared radiation with the cosmic microwave of the radio background. So you can have the visibility of the universe using the electromagnetic radiation. So the possibility to study the universe with neutrinos were recognized very far a long time ago by Maximilian Markov here with Bruno Pontecorvo, still in the 60s, and they said in a conference proceeding, he proposed to install detector deep in a lake or in the sea and to determine the direction of the charged particle with the help of the Cherenkov radiation, which is the main ingredient for neutrino telescope. Essentially, you have neutrinos which can interact. Neutrino can travel very large fraction of the energy, also the Earth diameter, and producing charged particle in the interaction which go upgoing, so you can see particle coming from bottom of the Earth. If you install a photon detector deep in the sea, you can, using the correlation, the number of photons and the position of the optical modules, recover the direction of the tracks, so also to determine the incoming neutrino direction. Of course, going deep in the sea means that in the sea, after, let's say, 30 meters, the solar radiation is reduced by a factor of 2. So when you go deep by 300 meters, the intensity of the light is reduced by 2 to the 10. In 3 kilometers, reduced by factor 2 to the 100. So there is completely deep, completely dark in the deep sea. So when you see light, the light can be produced by, for instance, particles which travel with a velocity larger than the velocity of light in the medium. For the water, the index of refraction is 133. That means that the velocity of light is 200,000 kilometers per second, and not 300,000. So charged particle of very energetic can produce light and can produce a signal. But of course, deep in the sea, you have also animals or biology activities which can produce light, and also radioactivity. So you should have some way in order to discriminate the signal and the background. But the main background for those detectors are the atmospheric particles which arrive, charged particles arrive on the top of the Earth. So the same protons and nuclei which escape the acceleration source can arrive on the top of the atmosphere, producing secondary. And in the secondary, you have muons, which can penetrate up to 10 kilometers water, and also neutrinos, and also neutrino coming from below, which produce a signal which is similar to that of cosmic neutrino, meaning neutrinos producing very close to the source. There is one way to discriminate the signal. Of course, you can observe an excess of neutrinos of cosmic origin from a given direction. So you should exploit the fact that you should have events in which you recognize with a very high precision the direction of the charged particle and then the direction of neutrino. or to measure the energy. We expect this is a sketch of a plot of the flux of atmospheric neutrinos as a function of energy. This green line represents the measured, this way, flux of atmospheric neutrino. The expected flux of cosmic neutrino is harder, meaning that at some energy, the cosmic neutrino should be larger in number than atmospheric neutrinos. And you can parameterize in a very simple way, just measuring the total energy of events, an excess of neutrino over the background, which can be parameterized with a formula in this way. So a normalization and a dependence of the flux as a function of energy. Of course, as the energy increases, the number decrease of events. So this is another way to see how important is the background. On the left part, you see the flux of atmospheric muons and atmospheric neutrinos as a function of zenith angle. So on the x-axis, there are positive values represent particles coming from above, negative value are particles from below. You can see, of course, atmospheric muons are only coming from above. The two lines represent the flux at two depths deep in the water. So this is the flux up to almost 1 kilometer, 700 meters of water, and this is in almost 4 kilometers of water. This is the flux of neutrinos, which of course are not absorbed by the Earth to energy. And this is the plot how the flux of muons reduce as increase the depth. So if you go deep in the water or ice, you reduce the number of background events from above. So since the proposal in the 60s, it took a very long time in order to develop a working neutrino telescope. It is not a history of the neutrino telescope, but just to say the final results. The IceCube detector was started in construction in 2006 and was completed in 2011. The IceCube was a telescope in the South Pole, which are producing the main results, which I will present in a few minutes. A second experiment in the sea, really an important step because it demonstrated the possibility to construct and operating for a very long time a neutrino telescope in the sea was the Antares telescope working from 2007 up to 2022. It's important because it covers a period of 15 years. Then there is a third experiment in a lake in Russia, in the Baikal Lake. And finally, there is in construction the KM3net telescope here in the Mediterranean Sea in 2 locations. Then there are, I have to mention that there are still activity ongoing for future experiment, one in the coast of Canada, and 3, there is competition between them, 3 Chinese R&D activities which plan to have at least one additional telescope in the South Chinese Sea here. So going to IceCube, IceCube was completed in 2010. It's made by 86 strings in the South Pole. The South Pole is made by ice. It's 2.5 kilometers of ice. There are holes drilled with hot water. I have a picture later on. And in this hole, you can deploy a string with many optical sensors like this one, which in the dark of the ice can detect the light produced by the charged particle. The advantage of this experiment is, of course, that the strings are fixed in position. The ice is frozen, so there are no possibility to move the string. While in the sea, of course, you should have the fact that the strings can move according to movement to the sea currents. So you have additional tools in order to calibrate the position of the strings in real time, which can move because they are 1 kilometer height up to 20, 30 meters. So you should calibrate in real time the position of the string in order to have a precision, the accuracy on the direction of the neutrino events with very high value. So this is a sketch. Of course, it's not possible to make a picture of the Antares telescope. I was really, I have an important role in this experiment. I am the deputy spokesperson of this experiment since 2014. So I the responsibility to try to push and have physical results from this experiment was made by 12 strings deployed here in the coast of the south of France. Each string is about 500 meters long and is made by a triplet of optical modules looking down going, because the main objective are to detect particles which are upgoing, which are free from the background of atmospheric muons. Neutrino can interact, but you know there are three different flavors of neutrino. There are electron neutrinos, muon neutrino, and tau neutrinos, and each neutrino, when interact with a charge current interaction, meaning they can interact by the strong interaction produce a charged lepton, which is the lepton with the similar flowers. One electron neutrinos produce an electron, a muon neutrino produce a muon, and a tau neutrino produce a tau. The three particles are very similar apart to the mass, and it is as an important consequence. The electron is the lighter particle, is the particle which releases the most fraction of the energy very close to the production point. So when you have a muon neutrino which interact, it can produce a muon. The muon can travel, for instance, 1 TeV muons can travel in water for 5 kilometers. So you can, because the size of the detector are of the order of 1 kilometer, you can have observation of muon which are produced 2-3 kilometers far from the instrumented volume. So you increase a lot the size of the detector because you can observe those particles which are produced far away from your detector. When the muon pass inside the detector, they can produce Cherenkov light, and the connection between the number of photons and the position of PMTs can be used in order to reconstruct a track with some precision of the order of 0.1 degree, is depending on the medium and of course on the energy of the neutrino itself. You can have also a muon neutrino interaction inside the detector. So the neutrino is entering the detector in the Kamiokande and Super Kamiokande languages that are called partially contained events, meaning that you observe nothing entering, neutral particle, and then some particle which go away starting from the center of your detector. And then you can have events like this one. You have a huge release of energy inside the detector because in this case, an electron neutrinos produce an electron traveling water distance of order of 10 meters. So compare 5 kilometers to 10 meters. So essentially, with respect to the size of the detector, in which the optical modules are 20, 30, 40 meters away, you see a sort of bubble of light which are produced in a limited region of the detector. So which is the consequence? For those kind of events, you measure better the energy. The detector works like a calorimeter, but not the direction of the incoming particle, because it's very difficult to reconstruct the energy, the direction of the part of the neutrino starting from this observation. So I mentioned IceCube, completed in 2010, produced a very impressive series of results. For instance, the first results was the observation of an excess of high energy events with respect to the background. As mentioned before, there are two different slopes for signal and background. For instance, this plot represents as a function of the reconstructed energy in the detector, the number of events, which are the data points in black, the background, this red and blue distribution at the background of atmospheric muons and neutrinos, which produce a signal, but with lower energy. You can see an excess of high energy events, which are fitted in the yellow region with a cosmic signal. Cosmic signal, as mentioned, is just a simple power law with a normalization factor and an energy dependent with some spectral index. And the fitting of the data produce, of course, one best fit point, which is here for the normalization and spectral index, and a lowered region, 90% confidence level, which is the circle here. So you have an expectation from a flux of neutrino not explained by atmospheric origin, so cosmic origin. This is again a plot of real events. This plot is a plot of an electroneutrinos producing this larger energy release in the center of the detector, this bubble. This is the energy estimate is of the order of 1 PV. Just to have an idea, 1 PV is 3 orders of magnitude larger than the 1 TeV. 10 TeV is the energy, the largest energy of proton in the Large Hadron Collider at CERN. So the energy of this neutrino is 2 orders of magnitude larger than the energy of proton at LHC. This is a second kind of events. This is muons entering from the bottom of the detector. The light represents also the timing. Red is earlier, blue is later. So is a particle which is traveling from bottom to the top of the detector. And from the amount of light, you can recognize the energy. This is the largest energy events in IceCube with about 1 order of magnitude larger than this one, 10 PeV. So also using those through-going events, so muons, IceCube observed an excess of events with respect to the background, which is this plot. You can see the reference over here. Again, you have data points at the background, and the excess of event with respect to the background is fitted again with a similar formula. It's the same phase space for the plot, but the normalization factor and spectral index are something slightly different between the two samples. Then there are additional samples. I will not enter in detail, but you can have a reference looking from this paper. Additional data samples are used by IceCube, but the result is similar. They always observe an excess of event with respect to the background. Maybe is not simply described by a simple power law. Maybe you have to introduce a broken power law or power law with different spectral index. It's not relevant, but the important thing is there are many evidence also supported by some data from the Antares experiment in the Mediterranean Sea. The Antares was very small with respect to the IceCube. It's about 40 times smaller than IceCube, but it was really important because now all the experience from Antares are moved to the ChemTriNet collaboration. Essentially, the 90% of the Antares members are inside the ChemTriNet, and ChemTriNet is redating all the, for instance, software and expertise from Antares. Just to mention the importance of this plot, this is essentially the plot I produced here. This is the results I mentioned at the beginning, in which we are putting some results in this empty space of very high energy of neutrinos and particles from the extragalactic space. So the objective is now to find something similar to the sky plot produced by the TV community in gamma ray astronomy. This is a very famous plot of the source present in the TV catalog of a source observed by the imaging telescope or other experiment like LASO or ORCA and so on. So it's the sky of object at energy about larger than 100 GeV. There are more than 300 sources from the galactic plane and outside the galactic plane. You can see also the division as a function of the redshift. If I have to produce a similar plot concerning the neutrino source, at present there are only 2 red dots in this plot, the red dots which are again from IceCube. One, the first very famous is this blazar, the T excess of 0.5 or 6, which was observed in 2017, and this triggered observation from two gamma ray experiments, one of satellite Fermi-LAT and the MAGIC experiment, which observed also an excess of a signal of gamma ray from the source in according to the same period in which the very high energy event was observed. This was an event of about 200 TeV, the reconstruct energy of the event. But IceCube itself, and in the same journal issue, in the two different articles, produce results of the analysis of neutrino events in the archival data of IceCube, finding an additional burst of event, about 13 events, plus minus 5 in excess with respect to the background. But this produces a sort of problem because during this period, in around 2015, there is no observation of excess of gamma rays, for instance, from Fermi-LAT. So the excess of event from this source was observed in coincidence with electromagnetic radiation for one event, without for a cluster of events observed of neutrino candidate observed early in the archival IceCube data. So there is not a simple theoretical interpretation for such kind of events. A second source was reported in a different analysis, an analysis in which neutrino are studied in terms of accumulation of candidates from a given position or region of the sky, using the fact that the events can be reconstructed with high precision. And the second source was this close by galaxy, the NGC 1068, which is order 10 megaparsec from the solar system, while the previous one was 100 times far away. And this plot represents, for instance, the data points as a function of the distance from the source on square degree. So you see an accumulation of events in excess to the expected background close to the position of the source. The excess was estimated about 8 events with 20 an uncertainty of 20 events. This means an excess of event with respect to the background. Which is the problem now? We have two sources, and again, you can plot because for each individual neutrino, you can measure, estimate also the energy of the neutrino. You can plot the number of events observed as a function of energy, and also producing a flux of energy from the source, because you know the distance, you know the sensibility, and so the parameters which represent the effective area, the quality parameter of the detector. So you can produce this quantity, which is the total energy emitted by the source for square centimeter per second from the two different sources, which cover two different regions in the energy. This is between 1 to 10 TeV, and this is for very high energy. So if there are some mechanisms which produce neutrino, the two kind of events seems to show that the production or the population of source can be really different. But there is an additional problem that I have to mention for this second source, the very famous TXS. This plot here is the official plot from the IceCube collaboration from this paper on Science, in which they present the results of an excess observing from this source in a period of 10 years, which correspond of 5 events. So this is the plot in which IceCube present a flux computed assuming, repeat, 5 events in 10 years. But in the previous paper in 2018, they found an excess of 13 events in 6 months. So that means that if you normalize and you produce the quantity on the epsilon axis, the flux is increased by 1 order of magnitude. And if you compare this flux with the total diffuse flux, this is again a result from IceCube. Diffuse flux means the plot I shown before, the integral of all events collected as a function of energy, you can see that you are very close to fill up to all the space, meaning that if the sources are transient or not is a very important question. If they are transient, probably the transient event produce all the very high energy neutrinos which are detected. And to observe and to decide if the objects are transient or not, you must use also additional information from gamma ray observatory, for instance, or additional experiment which can help to understand if the neutrino production occurs in a steady way or are produced in a sort of transient as those events. This is an open question. Of course, this is not an official IceCube results. This is my interpretation of the previous paper of IceCube. But I again presented this plot at the neutrino conference in last June in Milan. So the interpretation of the diffuse flux, so the origin of those events is an open question. If I enter in this discussion, I cannot stop without a short time. So I prefer to refer to this reference. Of course, there are many models in order to explain which is the origin of those neutrinos which are detected. Finally, last year, IceCube presented also an excess of neutrino from the galactic plane. IceCube is not in a good position for observing the central part of the galactic plane because IceCube is located in the South Pole. Of course, astronomers look the center of the galaxy going to the child or in the southern part of the sky, but for observing neutrino, you go in the opposite direction because neutrino are detected with a very precision way using upgoing events. So you should go to the north part of the Earth. So IceCube presented one results comparing the number of gamma ray which are observed from the galactic plane and try to see if there are a matching between the observation of neutrinos. Because they use different models, they produce different results. This is a plot, again, in a paper of Science of the last year, in which you can see which is the expectation of neutrino flux according to different models. But of course, the plan for a neutrino telescope in the Mediterranean is also to look from the galactic center with high precision. So the goal of neutrino telescope like IMTRINET is to produce a result from the galactic plane much better than IceCube, and I hope that the result will be produced soon. So this is the overview of the IceCube results. Of course, there are differences from ice to the water. This is a picture I mentioned before. This is one hole which is drilled in the Antarctic ice with hot water, and the optical modules, like this one, is inserted inside the string. So you have a larger number of optical modules, 40 meters, one from the other, so you can have an array of those optical modules. The difference from ice and water is there are many aspects. Ice is transparent. You can see, seems that ice is white, but at very high pressure, deep in the Antarctic continent, the ice is pressed, so it's totally transparent. It's much more transparent than water, but there are bubbles in the ice or dust, which in some sense are producing noise. They avoid to have a very good precision for the measurement of the direction of the track, because this pollution of the ice produces deflection of the Cherenkov photons, and so the reconstruction is a little bit worse with respect to the ice. But one of the main aspect difference is the main restaurant, the distance of the main restaurant. You should go to in the south of Argentina to find a restaurant. If you went to the experiment in Mediterranean Sea, you have a very good choice of location and also restaurant. You can take mention of this one. This is not one random restaurant. This is a sort of canteen for our collaboration in Capopastero. It's a very good restaurant, so you can book and reserve or take note of this one. This is a picture I did of one of the. Also, if you stay, it's very cheap, so it's a very good place. So this is a publicity for this experiment. This is a sketch of the construction of the chemtrail, which is made of two different experiments. One is called ARCA. The initial letter of this acronym means for astrophysics, while a second detector is starting with O, which is oscillation. So this is a detector for particle physics. The size of two detectors are very difficult. This is ORCA. The two objects are the Eiffel Tower, and this is, I lost my battle. This is not the Asinelli Tower, it's the Pisa Tower. This is the size of ORCA, and this is the size of the two building blocks of ARCA. And the location of the two are for ORCA, close by to the coast of France, close to the Antares experiment, while ARCA, that for astrophysics in Sicily. I will mention later only the results and the status of ARCA. The construction of the detector, this is a particle physics detector, means that the institution which collaborate are inside the collaboration also construct the experiment, or different part of the experiment. You can, the dots represent a different size in which different aspect of the experiment is constructed. For instance, here in Bologna, this is a picture of two bright technicians, this is Claudia and Giuliano, which are doing connection in the bottom part of the string. This is the containers in which all the information from an individual string arrive. There are optical modules and then connected to the sea. If additional information, you can see some movie from YouTube. And this is a picture of the size of the detector. You can see in the first part that one of the optical modules. The optical module of the string are contained at the launch. So when we must put inside the water, inside the sphere like this big one here, and then there is the unfurling of this the string and the optical module inside this sphere for a length of 700 meters in the case of ARCA, and each string contains 18 optical modules like this one, which is a sphere of this dimension with 31 small photomultiplier, which can see different region of the water to improve the angular precision of the measurement. In order to deploy the events, you need a bottle like this one, in which you can see one of the string which is going to be deployed. And you can see also a picture of the submarine, which is needed in order to have a connection deep in the sea. This is one important part of the experiment, because without the bottle, without the ship, you cannot do the operation. I have to mention that before 2022, the contractor was a Russian ship. Of course, after the war in Ukraine, this contract was dropped, and then we started a contract with a Turkish battle. Then in 2023, there was the earthquake in Turkey, and the battle was not available for a long time. So there are the problem for introducing this object in the sea. Picture of the phase of operation starting on one of the factories in which the string is assembled inside the sphere, and then the sphere is deployed in the sea. And this is the submarine which will do the physical connection of the string with the cable. And also you have a simulation of the unfurling of this sphere. This is a real movie of one of the string which is released. So the sphere now is going up, and this is recovered by the boat, the the ship, and then you have the string, which is in tension by a buoy in deep in the sea for a length of 800 meters. And then the remote operating vehicle is going deep close to the string and do the connection. This is the status of the experiment. The ARCA sites here in Sicily have now 33 strings connected. There are additional 25, almost 25 strings which are ready to be deployed, but we should wait the availability of the battle. And then there are 24 strings in the French sides. Of course, this experiment is mainly for particle physics to study some property of neutrinos, particularly the property connected to the neutrino mass. The telescope in the Mediterranean is complementary to the IceCube. This is the sky visibility. The blue region is the visibility larger than 75% of the time in the day, and the blue and the light blue is between 25 and 75. The IceCube has a different complementary visibility, but of course you can, those visibility is again for upward going events, which is the golden channel for neutrino detection, because you can measure with high precision the incoming neutrino direction, but you can observe also neutrino, as I mentioned before, looking from partially contained events or shower produced by electron neutrino. In this case, you can use neutrino coming from all directions, so the visibility of the sky is similar for the two telescopes. Of course, it is really important to have multi-message information, to have connection with external brokers or external which convey the information from outer experiment at ground or satellite. And just to mention, such experiment, IceCube, Antares, but also ChemTrinet, can receive information and produce and give information if there is a candidate close by to the direction triggered by the external event in 30 seconds, let's say, and because the data are collected and reconstructed in real time. One of the difference between IceCube and observing the water, that in order to have a high precision of the direction of the neutrino, you should weigh recalibration of the position of the optical modules. Remember, the sea current move the optical modules, and maybe you have a period in which the sea current are very low, but when the currents are high, you should use a calibration with some tools which are used in order to have a very high precision, so we can reprocess the data after a while. But the process, also the process of sending information, maybe you can are observing a very high energy events in real time, you should alert the external community, please look from this direction because we are receiving a very high energy neutrino, like the case of the TXS or 506 I mentioned before. And this is can be produced again in half a minute in the case of sending the information. Then I have to conclude with one particular event. So the ChemTrinet telescope is in construction, meaning at present we are 33 strings in operation, but in the past we have period from 6 to 15, 19, 21, and 28 strings in different periods. And the policy of the collaboration is to analyze the data at the end of the period. So when completed the period of 21 strings, which is a period from September 22 up to September 23, we analyze the data. And so there is at present no possibility to send information in real time just because we are in the construction phase. But, and also because we need the calibration of position energy, we wait up to end of the period in order to analyze the data. So when we analyze the data of the 21 string period, and the ingredients is to have a detector working a very good way and with a larger number of domes. Domes is a digital optical module, is the sphere. And in the sphere you have 31 small PMTs. So the total number of PMTs is the number of dome times 31. This is produced this larger number of PMTs still in the water in this period of time, and also to have bright PhD students. So sometimes the old professor like me have the time to follow the directive of the director of department and to have the duties or didactics, but you should have a bright student which can analyze the data. And those bright students can find one event like this one and going to the internal presentation, weekly presentation of our group and saying, so analyzing the data, so you can see this bubble here. I found an event here. This event is plotted as a function of the zenith angle. So again, -1 represents events from below, 1 event from the top, 0 are events close to the horizontal. This is the number of PMTs which are involved in the events. So just to have to mention, this line here, which is almost invisible, represent the line which contains a 99.9% of the events, or only 1 per mil of events are above this line. So this is one of the teaching activities I'm involved, so sorry for that. So you have a large number of events which produce a large number of triggered PMTs from above, which are atmospheric muons, no problem for that. So neutrino candidates with energy distribution we must study, but this is an event on the top which is astonishing. So probably we suspected another problem. Sometimes in the Antares experiment, I mentioned it many times, Antares was the prototype, we found events in which production of light do some hardware problems. We recognize that we have a method in order to see the problems. But it was not the case for these particular events. I will show the reconstruction in an animation in the next slide. And in order to understand which is the probable energy of this kind of event, we produce a simulation. Of course, the number of PMT which are involved is a proxy for the energy of the event. Of course, each hit contains also the information of how many photons are arriving, because each PMTs can have not only give the information, hey, I received some photon, but how many photons? Of course, there is a saturation. So most of the PMT which are very, very close to the track are saturated, but you can see the light also for PMT which are far away. So you can have additional information to reconstruct energy, but just using only the number of PMTs, this is this black line, the arrow represents the number of PMTs involved in this event here. The two colored plot here represent the simulation of events with energy of 1 PV. This, don't know the color is the white color is 1 PV, meaning IceCube has 1 event for year, roughly, of this kind of energy. And you can see you are very far from the number of PMT for this particular event. This is the simulation of 10 PV events in our detector. And this means you are simulating many events with the same energy. And this is the distribution of the number of photoelectrons. This is relevant because you can have also the information as how wide is the energy resolution. So when you should mention which is the probable energy of this event, you should consider that the distribution of monochromatic events are like this one. So the only conclusion I can say now is that this is a multi-10 PV events. So it's much the energy is much larger than the energy of 10 PV, which produce in IceCube 1 event in 10 years. So if really astonishing events, and this is the animation, so you can really see that this is a track. The information of individual PMTs is not only the number of photons, but also the arrival time. So you can reconstruct with high precision the direction of the incoming muon, the particle which is entering, sorry, inside the detector. This is the side view, and this is the top view of the detector. You see also flashing PMTs after the passage of the particle. This is an explanation. The particle is almost horizontal, is 1 degree above the horizon, but this is again expected if you consider that this is an event with energy larger than 10 PV. This plot is complicated, but the different color represent as a function of neutrino energy in GV, and the zenith angle from below, so this is 90 degrees, the horizontal, 180 is the bottom of the Earth. You can see the transmission of the Earth for neutrino. So when the neutrino is below, let's say, 30, 40 TeV, all the neutrino are passing the Earth. You have no absorption, but at, let's say, 100 TeV, neutrinos start to be absorbed from the Earth. And when you go, just using simple formula for neutrino, which are many PV, you can also expect neutrino from the horizontal plane, which the path length is not too much in material. So this is additional information about the strings. For the string closer to the event, this is the reconstructed track. You can see the number of feet and as a function of the time. So there is a peak very close to the passage of the muons, the direct line, and then you have additional hits which are produced in second time. And of course, those information are used in order to reconstruct the energy. The event was presented again in the major conference of this year, which was Neutrino in Milan, and produced also some news in the newspaper and some rumors. And this is from the release from news from this conference from Nature. Of course, now we are producing detailed information and producing a paper about this event, which was accepted by this journal. We hope to have soon some information, additional information. And these, again, are the number of photons, entries mean the number of PMTs which are involved in the events, as a function of the distance of the track from the entry points. You can see additional peaks, and those peaks are consistent with the fact that at very high energy, muons start to become as an electron, meaning that there are also stochastic production of secondary shower along the track. And you can also reconstruct, due to the granularity of the detector. It means that for each optical modules, we have the 31 PMTs which can receive the information of time and number of photons which arrive. You can have information of additional cascade producing along the direction of the tracks. So you can recognize that the fact that during the passage of the particle, you have secondary cascade, like those produced by an electron, which are starting to produce light, and they can be seen. You can reconstruct the position of those additional vertex along the tracks of the muons. So it's another way in order to say this is a real through-going particle which passes for 1 kilometer length inside the detector. It's not an atmospheric muon. It cannot be an atmospheric muon. We reconstruct the direction of the particle, and for the larger fraction, it travels inside the rock. So the quantity of matter to be passed is very, very high. And for instance, this is the estimated quantity of material, minimum quantity of material to pass, which correspond 140 kilometers of a material with the density of water. And this is the simulation of the, assuming some optimistic value for the flux of muons, which is the probability that a muon from atmospheric origin that produced by charged cosmic ray can arrive at the detector. So essentially, it is impossible that muons produced in the atmosphere arrive in the location because the quantity of material to be passed is too high. So the only possibility is that neutrinos are interacted in some points during the trajectory, and maybe very close to the detector, 1 kilometer from the detector, and produce the muon which is passing. So why is so important? This is again the plot I presented, and again in this context is the plot I used in order to produce these results. Now you have at higher energy some kind of terra incognita. You have no information about the fact that particles are existing here. Of course, you have a charged cosmic ray. You expect some secondary neutral particle in this region, but as I mentioned, you have no way in order to measure photons in this energy region because they are totally absorbed by the radiation present foreground radiation present in the universe. You have models and upper limits so far. So the line here are some theoretical models about neutrino production. Again, I don't enter in discussion. And there are also results upper limit from IceCube. Of course, you expect that the events I mentioned is at least 1 order of magnitude larger than the most energetic event of IceCube, the event I showed before, and is represented by this spot here. This is a data point which represents the expected flux using the fact that you are observing 1 neutrino with this energy in, let's say, 10 years of IceCube data taking. Because we are observing neutrino for a smaller period of time with ChemTriNet, and the energy is at least 1 order of magnitude larger than this one, you should expect 1 data point somewhere in this region, and maybe also above the upper limit of IceCube. Again, because the period of time is not 10 years, but is smaller than 10 years. Of course, maybe a situation similar to Kamiokande in 87. Kamiokande is working still today, is a larger size, is now Super Kamiokande, but no supernova events are observed since 1987. Maybe it's a situation similar to this one, but of course, if the data point is here, is a physical process which can be different from the production of neutrino of those energy, which the number decreases as a function of the energy. Of course, there are models. The fact that there are curves here is the fact that you have theoretical models that predict the existence of neutrinos of such energy in this energy region. So going to the conclusion, this is the last slide. I don't know if I'm in time. In my point of view, working on astroparticle physics since my thesis laurea, multi-messenger astrophysics is a really important field trying to join the activity of different community, that of particle physicists working, studying the universe with neutrino gamma rays, and gravitational waves, and gamma rays, and astronomers. Of course, we are looking at different aspects of the universe. Electrons produce some kind of signal, protons produce a different kind of signal, and one interesting thing, it seems that the extreme high energy universe seems to produce more energy in terms of neutrino than in gamma rays, also taking into account the possibility that the gamma rays are absorbed. And also a significant fraction of extragalactic IceCube signal seem be produced by sources which are not emitted, non-emitting gamma rays. So the two sources are, of course, from objects which are known, but still the events in the TXS are producing gamma rays in some kind of, one particular event not producing gamma ray in the bursting events observed in 2015. So ChemTriNet Observatory is an increasing detector. For instance, the founding for the completion of the 1 building block of 115 strings is already assured. As I mentioned, now essentially 1/3 of the experiment is working and working well, producing exciting results, as I show. We are additional 25 strings which are ready and we just wait to have the opportunity to put in operation deep in the sea. But the funding for the construction and completion of the one building block is assured. So we hope if there are no problem to have the full operation to the detector in operation up to 2028, and it will operate for 10, 15 years for a very long period. We have these extraordinary events of very large energy. Of course, we produce a lot of excitement in our community, and we think this is a very interesting event. We will try to have information as soon as possible. But one aspect, just to conclude, today we are studying the universe because this is still an open field. Of course, it is a very, also if there are 10 years in which we are studying the universe with neutrinos is in a very still preliminary way. So you see the catalog of gamma rays source is very large, contains hundreds of events, and now we have very few and mysterious events which enter in the sky of neutrinos. But in the future, we hope to have some characterization of this, the object which produces neutrinos. And of course, we have a cosmic accelerator which can be used in order to test also some particle physics which can never be studied also by future accelerators. So the integration between the community of astrophysics and particle physics, in my opinion, is really important also for the future. I conclude my talk, and thank you very much for your attention.
Thank you very much, Maurizio, for this great lecture. It was really a lecture on Newton astrophysics. And so it is impressive how much astrophysics and physics, engineering and technology and also adventure is in these great enterprises. I also, of course, appreciate your remarks on the restaurant. This is, I think, most of us. So, yes, so now we have time for questions. So please don't be shy and ask questions. Yes.
Well, thank you for the nice lecture. You surely thought and checked already for this high energy event, whether it could be associated to the boat, I mean, the brightest of all times gamma ray burst, which happened in October 22. And if not, well, and in any case, what are the limits on the neutrino flux from that event? And if that makes sense or not?
Of course, we have tested if there are association with some no events. Of course, I am not allowed to mention which is the date of the events, but of course, we are still in embargo phase. So I can just mention that is between September 22 and September 23. This is the so you have a very large number of events occurring in this period of time, but of course we can recover the direction because we are, so if you see the literature, of course, you can see that we are producing papers about the connection with these very bright gamma rays with no observation with the neutrino telescope, either from IceCube and chemistry. So there is no, and of course the plan to have a connection with gamma ray is one of the important things also for the future. There are papers in which some models and the optimistical model are excluded, but one of the possibilities, in my opinion, still open for production of a very energetic neutrino is still this of the gamma rays. So of course, of the gamma ray burst, sorry, of course is one of the plan of the experiment to have as large as possible connection with the observational gamma rays burst.
Thanks for the talk. I'm wondering if you can say, if you can speculate a bit more on what kind of constraint you can get on the oscillation of neutrinos and the related mass and hierarchy.
Okay, this is the goal of the other experiment in the south of France. Essentially, concerning neutrino oscillation, now there are many experiments done by accelerator and experiment close to reactor, which constrain the parameter of space for neutrino oscillation. So some experiment can measure better the oscillation parameter. One of the things which can be done with those experiments, either in the South Pole or on the water, is to study the effect of neutrino oscillation passing through the matter of the Earth. So there is some difference behavior of neutrinos and antineutrinos, and this the difference between neutrino and antineutrinos also from muons and electron neutrinos during the passage of the Earth can provide information about the fact that the hierarchy of the neutrinos. So we know that there are three flavors: electron, muon, and tau neutrinos. The of the three neutrino eigenstate for concerning the mass, which are conventionally called M1, M2, M3, or nu1, nu2, and nu3, with different mass. The information we are missing is that if the neutrino 1 is the object with a lower mass, or is the object with a higher mass, which are some important fact concerning electron neutrinos. The linear combination of the eigenstate of neutrino flavors and mass say that electron neutrino is mostly composed by neutrino of one type. If the neutrino 1 is the lower mass, some of the measure for future measurement for neutrino properties, as the fact that the neutrino are Dirac or Majorana particles, are really difficult, while if the mass 1 neutrino is the highest mass of the three, the things are much easier. So the possibility to study the mass ordering of the three neutrino flower is possible studying the different behavior of neutrino and antineutrino passing to the Earth. Of course, the mathematical involved is not simple. The observations are not simple. You need also probably different information from different experiments. There are not, the KM3net ORCA is not the only in the world trying to do the same things. There are other experiments in China, for instance, the June experiment, which is a very huge balls sphere filled with scintillator in order to do similar study. So it's a difficult task, but for particle physics, it's really important to know which is the ordering, the mass hierarchy of the neutrinos. I don't know if I've answered it in some sense to your question.
So that IceCube and ORCA are complementary in visibility. I guess it's a good thing, but on the other hand, probably it means it will take some time before some energetic event is observable by both. Is there any expectation how long before observing something very energetic with both?
Of course, it's almost impossible to have the same events observed by the two. So probably you can try to see if there are some source producing very high energetic neutrinos, which can be observed by the two detector in an independent way. And this, of course, is still in operation. We are in contact. We have strong connection with IceCube, already with the other experiment Antares, in order to match if there are events coming from the same direction. Of course, you cannot see the same neutrino from both experiments, but you can see doublet, so two events from essentially the same region. So far, there are no events which are coming from the same object with very high energy. Of course, this will be a signature, very important signature for the existence of a neutrino source. Another possibility which can use the information of just one experiment is the observation of tau neutrinos. So tau neutrinos cannot be produced by cosmic ray in the atmosphere. Energy is too low. The process of producing tau neutrino is essentially producing very few tau neutrinos, but tau neutrino can be produced by oscillation of neutrino, energy neutrino from extragalactic or also galactic origin. If you observe a very high energy neutrinos and you identify the signal due to the tau interaction, of course you are almost sure that this neutrino is of cosmic origin and is pointing to a particular source. So the search for tau neutrinos is another, of very high energy tau neutrino is another important, which is essentially almost similar to observing pairs of neutrino from the same direction.
Thanks.
Very nice talk, very interesting. But I have a question that's more logistic rather than astrophysical. How do you deal with the sea sediment and
With the
sea sediment or like seaweed on the detectors?
So this was one of the aspects which frightened very much at the very beginning in the Antares case. So we found that sedimentation biofouling on the sphere is very high on the top of the sphere. So in fact, in the case of the optical module of Antares, there is no sensible part of no PMTs on the top of the part of the sphere. In case of the ChemTrinet, there is a fraction of the sphere which is not covered by PMTs. But in fact, we found using the 15 years of Antares that the problem is partially reduced due to the sea currents. So you have deposition, but the fact that the affluence of the water due to sea currents sometimes wash and reduce the biofouling. So the effect was at the very beginning was a very large problem for the upper part of PMT. The bottom part do not suffer problem essentially because you have no deposition on the top part. But also we found using the information from Antares that is not so dramatic as expected at the beginning. Of course, we have some reduction of the sensibility on the top part in a time scale of years. And for instance, for Antares, we published a paper in which we reduced the problem, increasing a little bit the voltage on the PMTs in order to maintain fixed the sensibility of the instrument. So there are some tools in order to reduce the problem, but the problem exists, of course, in water. The main problem is that you need to calibrate the position of the object. And just to have an idea, in order to have the precision of 0.1 degree on the reconstruction of the muon direction, you must know the position of individual optical modules with a precision of 20 centimeters. And we found that due to the sea currents, you can have a movement of the top part of the string up to 20 meters. So if you have no calibration of the position in real time of optical modules, you are totally wrong about the reconstruction of the direction of the particle with high precision. So we have tools in order to have information every 2 minutes of the position of individual optical modules and they recover the position. The flux of the seawater is not so high, so you have programs which reconstruct the position of the individual PMT on the string using these calibration tools.
Okay, I'm looking back, going back to the astrophysical counterpart of neutrino sources. If I understood that there are two possibilities. One is related to the jet, like in the case of TXS, and the other case, NGC 1068 to something else. People are talking about accretion disk. So my question is, I was curious about the flare that was observed in TXS, and that flare was not observed in gamma ray. So there is any speculation about the fact that this flare is related to the processes working in NGC 1068? I mean, is due to the accretion disk?
So you can try to have a diplomatic answer. There are a very large discussion about the production of this kind of, in my opinion, the situation is not clear. It's not totally clear. I can try to discuss a lot, and there are many papers, but essentially the situation for this particular event is not totally clear at all. I try to be diplomatic with this.
Okay, other questions for Maurizio? So if not, I think we can thanks very much again, Maurizio, and wish you Merry Christmas and Happy Christmas holidays to all of you. So thank you very much for coming. We have just here in the hall the toast, Christmas toast of our institute. So everybody, I think, can join. Let's hope there is a slice of panettone for everybody, but just or some small wine. Thank you very much. Thank you very much again.
Grazie mille. Spero che il taglio...